about Gestalt principles, and then we'll talk about data. But before we start, any questions about the homeworks? Any questions about anything else administratively?
Where should we go to learn about best practices?
Best practices for
SVG and
yeah, you can look at our reference solutions, but best practices are, like I'm basically hinting at them in the lecture, but this is something that isn't quite as easy to, there isn't like a resource, right? This is like we could cover something like that in a full software engineering class, but here we're really only covering like, this is how you can do it. We don't really have the time to go into best practices. Yes?
So do style attributes count as like inline styles? Or
say that again, please?
Do style attributes, are they considered like inline styles?
I would say, like, if you want a style position by a style attribute, like basically, no, because everything that, so let me put it this way, everything that is unique for like a specific object, like if you want to do a dot in the scatter plot, then you can, you can use that as a style as well, even though you should probably use attributes, in my personal opinion, but this is a preference, right? And if everything that is consistent for like a larger group, like the color, all of them are red, that should be like a style that you have somewhere else.
Okay, so are we no longer constrained to one class name?
Yeah, we actually posted an announcement about this, right? This was kind of like a leftover sentence from a previous version of this one.
Okay.
You can, like if you ask about red-blue color, you should use two classes for that example. Okay, so let's talk about pop-out. What is pop-out? Pop-out, they're also called preattentive properties. They are properties detected by the lower level visual system. And this is something that works super quick, like 200 to 250 milliseconds. You will see whether there is something that has a pop-out effect on the screen. They're also very accurate. You are basically guaranteed to see a pop-out property on a screen. They're also processed in parallel, so I can easily spot 10 pop-out attributes in a scene. And this happens before our focused attention, so I don't really have to go through items on the screen serially to perceive them, and that's why we call them preattentive, even though that term isn't like in common usage anymore in the psychology literature. Paying attention is of course important for cognition, and so therefore this is even like happens before cognitive processes. Another thing that's cool about this is that it's independent of the numbers of distractors. And it kind of like the opposite of a preattentive property or a pop-up property is if a property requires serial searching, so where I have to check every instance of an item to see whether it is of a certain attribute. And so this now sounds a little bit theoretical. Let me give you an example. What is like unique about, like, can you find one point that is odd here? Yes, there's a red point, right? So that's very, very easy to see. And this is basically, it doesn't matter how many blue dots I have here, you will still see the red point immediately. So this is like what I mean with preattentively. So we can clearly distinguish between like has the stimulus and doesn't have the stimulus. There's also one, right? So you kind of saw the shape. Here's a circle in a sea of rectangles. That is another preattentive feature, but you might have noticed that it takes a little bit longer. So not all of these features are equal. So that was interesting, right? So we had a couple of features. We had curvature, we had shape, we had size, and so on. The point of this one here is like, what's the unique feature here? It's a red circle. So it's a combination of two pop-out features, like shape and color, but that doesn't work, right? So we can spot like this only along one dimension. We cannot do like combined pop-out features and hope that they would actually pop. So here's the red circle that you probably all spotted, but what you did here is that you went through this, like skimmed all of the elements and then kind of like put in like a higher level cognitive process to distinguish the one here from the other ones. And so you have to do some serial search, and if I gave you many, many more elements here, and only one of them would be this combined distractor or this combined feature, then it would take you longer to spot that one. So here is this example, conjunction targets. These are not a unique visual property when the distractor objects have both properties. And so here is a summary of some preattentive features. Like we have orientation, length, closure, size, curvature, density. So here we have a cluster, hue, color value, or brightness up here. It's less strong here. Here my GIF is a little bit broken. This is supposed to flicker. And then direction of motion. So like motion and things like flicker are pretty strong preattentive properties because our visual system is also trained to detect motion. So what are the kinds of tasks that this is useful for? First, we can do target detection, right? Identify the presence or the absence of a specific target. We can also do boundary detection. So if we have like a group of red features and a group of blue features, and they have a clear boundary, we can easily see that. Then we have region tracking. So for example, if elements move together as they in time and space, so we can move one or more elements with these unique features in space. And we can actually do pretty good counting and estimation. So you get, like if I give you 5 red circles and a sea of blue circles, you get a good sense of how many items are red. So like here are some examples. The number estimation tasks, like we notice, is like somewhere between 5 and 10 immediately, and we can clearly identify the boundary here on the right side with the color hue. There is this hierarchy, as I already mentioned. These preattentive features, they are like not all are created equal. So we have here like a couple of cases. In the first one, you see very clearly the hue stands out well. Then we have this hue on the right side. We see that we have the shapes, but it doesn't pop quite as much as a hue combination here. And then if we have rectangle and then other hues, this might be even harder to detect. So basically, like color hue is a very strong preattentive feature. Other things are not quite as strong. So why do we care about this in visualization? We can use this to draw people's attention to areas of interest, right? So for example, if I search for an item, and that's what happens if you use something like a PDF viewer and you search for an item, it will color the target where you can find the item. It will use this hue to highlight that item, and so you can quickly find it. It can be used to express similarity or group membership. So like I can highlight all the items that belong to a certain group together. And the thing is though that I have to be quite careful about designing those visual features. We kind of learned this from these conjunctions and also distractors. Like it works if we have red over blue, but it doesn't work if you have red over blue and green and violet and so on. So if there's like a sea of different colors, then we cannot use color anymore as a pop-out feature. I'll show some examples of that later. But yeah, essentially you also need to avoid conjunctions. And so like this pop-out property is one of the reasons why when I design visualizations, I try to absolutely limit my use of color, because then I can use highlights very effectively. Compared to if I have a very colorful visualization, how do I do highlights later? Okay, so moving on to the next topic, change blindness. And change blindness is, like I showed you this video about attention blindness earlier. Change blindness, remember when the person asked for directions in the first lecture? Change blindness is a similar interesting effect. So it turns out, also recall that how our visual system works, right? And that we kind of like pay attention to something specific and don't see the whole scene at the same time. So it turns out we can also not remember details of an image across separate scenes. The only exception to that is something that we explicitly focus our attention to. So if you, for example, let's say, if somebody's shirt color here changed, or somebody put on a jacket while I look away, I would probably not notice, right? I would only notice if I really looked at this person before, or see them do it. So this isn't really like, this change blindness isn't a failure of the vision system. It's really more a failure of like inappropriate attention guidance. The thing is that an interruption, like me looking away or blinking or an isolate or a blank screen, amplifies this effect. And so what do I mean by this? Like here you have two images that are interleaved by like a blank screen. And those two images have a difference. Raise your hand if you can spot the difference. 2 people, 3, 4. Yeah. We're somewhere in the neighborhood of 10 people. So what you had to do to actually see that is you had to focus on a specific region of the image and then see whether something changes. Right? And what is changing here is the shadow of the helicopter is gone in one of the images. So here's another example. Raise your hand if you can spot the difference. This one is actually even more obvious. Still, we're like at 10% of the class seeing it. So yeah, if you don't have this distractor stimulus, you can very quickly see that, right? And here's the final one. Again, raise your hand if you see it. The object in this picture is very important to the concept of the scene. So look at the engine. So what happens here? There's kind of various theories. I don't want to go into the detail. I put a link into the slides for you to read up on this. But what are kind of like the influencing factors for that is our attention. So if I, like here in class, I tell you, pay attention, something is changing. This is kind of like the worst case scenario from if I try to get something by you, right? So you're really paying attention, you're really trying to catch me fooling you. But if you're not aware that something like that will happen, you're even more susceptible to not noticing the change. Of course, the semantic importance of the changed object. In the previous scene, if the whole plane were to disappear, or if we have like only a single person in the picture and that person disappears, then that makes a big difference. And it turns out that we are really good at overlooking low-level properties of an object, like for example, like color. Like if we kind of like the semantic concept, if that is retained, we might not spot it. Here is another example of like without any. This is just a gradual change that is happening. So I started it now. And now this gradual change is complete. Well, now it's complete. I got nowhere to look. So I'll play this again, and if I hit back, it will flash back immediately, so you might be able to spot it. So I'm playing this again, and you see it gradually being removed here. So such a gradual change is hard to recognize. Here's another example. So, it's like a big rock here in the foreground. this is being added in that case. Here's one, like a beautiful scene from the 80s. So, anybody spotted it? The left lady's shirt color changed. Okay, so I'll reflect a little bit on why this is important for visualization after I covered attention blindness. Attention blindness is even like more amazing, in my opinion. I'll show you a couple of videos here.
This is a movie perception test. Watch this brief, silent movie, and then I'll ask you some questions about it. You saw a person get up from a desk to answer a phone, right? Did you notice anything change during the video? The video had two different actors wearing different clothing. Watch it again. Most people don't notice the change, a phenomenon known as change blindness.
Here's another video.
This is an awareness test. How many passes? The answer is 13. But did you see the moonwalking bear?
Okay, and one final video.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's gold below stairs, sir. I was planting my petunias in the potting shed. Constable, arrest Lady Smythe. How did you know, madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you? Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's gold below stairs, sir. But I was planting my petunias in the potting shed. Constable, arrest Lady Smythe.
So this was a campaign for watching out for cyclists by a London agency. But of course this applies to when we design user interfaces as well. So the take-home points, why do I show this to you other than to entertain, is we really like to find meaning in what we see in a visualization. We must selectively pay attention to what is important. And our low-level vision is really driven by some basic object features rather by a conscious effort where to look. So things like pre-attentive processing, and especially at this point here, our attention is driven by pre-existing knowledge, by some expectations and goals stored in long-term memory. So as visualization designers, we have to be quite careful about not doing any subtle changes in our visualization. Right? If we want a user to notice something, we need to make this explicit. We can't be like change the color slowly and expect them to see that. So the last section of perception lecture is about Gestalt principles. And Gestalt is like a German word for like the appearance, the form, the shape. And this was kind of developed by Wertheimer and some of his colleagues, like in Vienna around 1920 as part of the psychology movement back then. And there are some recent extensions to it, like in the 90s and so on. So what is Gestalt? What are Gestalt principles? They're described as patterns that transcend the visual stimuli that produce them. So there's two examples down here. You actually see a circle and a rectangle, right? Even though what you see or what is on the page isn't really like a circle and a rectangle, it's just segments of this circle and the rectangle. And so you've probably heard this quote, the whole is greater than the sum of its parts. And this is kind of like what this gets at. However, Kurt Hofka, who is one of the Gestalt psychologists, really had a different way of thinking about this. He said, das Ganze ist etwas anders als die Summe seiner Teile in the original German, which translates to the whole is something else than the sum of its parts. So it's not better, right? It's not more, it's just different. And that is his point that he wants to make. This quote is usually attributed to Aristoteles. So what are the Gestalt principles? So we have proximity. So for example, here, like proximity is a very strong grouping principle, and we perceive, like this here is like a uniform grid, we perceive this here as rows, right? By making those two items in close proximity, bringing these items into those rows in proximity versus having higher proximity here, we perceive them as groups. And so proximity kind of like is even stronger than any color pattern. So if I asked you, like here, what are the two groups? Most of you would probably say the left and the right. Very few of you would say the orange and the black ones, right? And so here's like an animation of like how we can change, how we can use proximity to change kind of associations, like between 4 columns or 2 cards or 4 cards in this case. We can use proximity, essentially, this is kind of like what we look for, right, when we look at patterns in data. So it allows us to group items by placing entities in close proximity. And so if this were a scatter plot where we have some data values, we would say the items that are in close proximity, they are similar in some way. We can use like other visual attributes to express the similarity, like colors and shapes. And similarity is really really modulating the color scale here. Here's another example of dissimilarity, like how an item is dissimilar, and therefore we focus our attention on it. And have an example, we can co-modulate color, shape, size, value, orientation, or texture. So here are 4 different examples. Here I have co-modulated color to say those 2 items belong in a group. Here I have co-modulated shape, color value, and in this case here, I have actually added a glyph to it. And like repeating what I said earlier about when I talked about pop-up, it's very good for like 1, maybe 2 colors or 2 properties simultaneously. Here I can spot the red dots very quickly. I have the same red dots here in a field of distractors, so that doesn't work anymore, right? This comes back to my design guidelines of like minimizing the use of color and visualization so that I can leverage this pop-out for important pieces of information. It is also kind of like, it depends a lot on the clutter in your environment. This is a screenshot where I've highlighted a couple of spots in this combination of web browsers with red. So you probably all spotted the 3 ones in the text here fairly quickly, but then in the map we have more clutter. There's 1 dot here, and then here in this image I have low contrast another dot, right? So that's difficult to spot. The size of the object is relevant, how distinct it is from its background, how cluttered the background is in general. The other way to express similarity is also to modulate everything else. So for example, if you want to, instead of color highlighting those two items, I could just blur out all of the other items. Or I could darken everything around it. You might have seen this darkening in things like the Microsoft Windows user account control, right? They really want you to pay attention to the security pop-out box, and so they not only like put a pop-out box in front of your nose, they also darken everything else around it. And these are some examples of how, from academic papers, how people have studied like recommended buttons to press next with these kinds of like graying everything else out, or here brushes by like highlighting shared items by blurring everything else. So these are tricky things to do, but in some cases, like especially this darkening around a specific element can be useful. So I'll run another little experiment with you guys. We have grouping by proximity, grouping by color, grouping by size, and grouping by shape. Okay? So here, what are the groups? Top and bottom, left and right, left and right, left and right. Okay. What about now? What are the groups here? Exactly. So this is, now I've kind of overridden everything, right? I've used proximity, and just by adding these lines, by adding connectedness, I have said, like, this is more important to me. So this isn't an original Gestalt property that they discussed in the 20s. This is something that was really only studied in detail in the 90s. And so connectedness could be like a line, a surface, or an outline that is shared between different items. And this is a very, very strong, like say, primer to identify things as a group. Similarly to that, like here we have proximity is the strongest one. Then here we have connection as the like overriding the strength of the proximity. And here, like we probably have a hierarchical perception of grouping, right? We understand that the items are grouped or connected by their grouped by their connections, but the enclosure on top of it tells us there's a second level grouping as well. So here's an example of like first a scatter plot, and then using connectedness to like highlight. Like actually, it's pretty hard to see this as a two different time series if I just have those rectangles and circles here. But if I do connect them with a line, as in a line chart, it's very easy for us to spot, right? And then I can draw more attention and group those items by using something like an enclosure in this example here. So you can use common region to basically group items that are not necessarily in very nice disjunct spatial regions. Like here, we have these like pretty scattered elements, but as soon as I throw a frame around it, we have, of course, grouped it successfully. Here are some varieties from research papers at Viz that used connectedness to visualize set relationships on top of a map. So this would be, imagine these, like the green ones are restaurants, the orange ones are hotels, and the violet ones are like subway stations or something like that. And so here we have like a hull on the left, then we have a continuous line in the middle, and then like a branching line, kelp diagrams on the right. It's just like where you see these kinds of principles appear in visualization research. Each of those is like a visualization paper. Another Gestalt principle is continuity. So what do you see here? A square and a circle. Anybody see anything else? Pac-Man. Yes. Pac-Man. That's good. Like, we don't assume that the circle is any of those, right? We don't assume this is just like a pie chart or a segment of a pie chart. We don't assume that the circle has this kind of shape or some kind of like completely discontinuous shape or weird shape, right? We kind of like assume good continuity in a shape that we cannot completely see. So here is an example where we assume continuity by simply like arranging them. We kind of see these lines appear even though there are no clear lines. So continuity, like here's another example of this, right? Here we would perceive this as two objects that intersect, but we usually, like this is what we would think that this graph means. This isn't really what we would think that this graph means, right? So like it is ambiguous. Like you can like legally divide this if you don't have any more information into those two shapes. But again, our environment of like how nature works kind of tells us that the left one is the right solution versus the right one. And so here's an example of how this applies in visualization, right? If you have a node link diagram like on the left here, and you use discontinuous shapes, they're a little bit harder to follow than if you have those continuous shapes. We kind of like use this for these. This is different from like the Dalmatian that I showed earlier, right? Here we actually are like we're not using any distractors. We just like don't show like the outline or the contours of the object. We simply hint at where good continuation would complete an object, and we are perfectly capable of recognizing all of these objects or faces. And we can even do like kind of infer complex shapes with a fairly minimal outline of those shapes. So like we don't need a lot of that. Another feature that we assume is symmetry. Like we like to have things be symmetric. Like our faces are symmetric mostly from a central axis. And so this is something like we wouldn't perceive this as a figure. We would perceive those two here as a figure. And if we had a compound shape like this, like two different shapes, we would assume like this object here to be symmetric and not to look like this. And this is a feature that we can kind of leverage because we're good at spotting symmetry and asymmetry. And so this is something that you would do in a population pyramid, for example. Like population pyramid shows the distribution of age in a population. Here we have two different populations for Finland in 1917 and 2006. And we can spot where we have outliers up here. We kind of see the trend we expect that women tend to live longer than men. We can spot that fairly easily. So if we showed those two like side by side, both aligned to the left, something like that would be a little bit more tricky for us to spot. And then like another thing that Gestalt theory tells us is that somehow we separate figure and ground. And these are some examples where there's like a little bit of an ambiguity about what is the figure and the ground. Right here, I either have a drinking cup or two faces, and then here we have like a continuum between fish and ducks, for example. So this is MC Escher pictures. You've probably seen those before. So how can we like use this to articulate figure and ground? Here is an example. So here we don't have a separation, but if we like modulate our backgrounds, then we can very clearly see this distinction here. Okay, so let's reflect a little bit on like here is the scene that I showed you before. I want to use pop-out effect to highlight something here. This is actually from a paper that some colleagues and me wrote in 2011. And so we studied how can we use search, and how can we highlight items in search so that they're both very visible, but also don't distract from what is on this screen. And so the first thing we tried blurring, right? Who can spot some items here? It's kind of tricky, right? There's fishing, there's general. I said earlier there's this dot in here that is almost impossible to see. Darkening everything else works reasonably well, right? We can see many of those spots, but it might become harder to read the background than to really perceive the background. Then here we had like the color highlighting, as I showed it earlier. Here's an example with blinking, which works fairly okay, but it's pretty annoying. And then we tried what we called these visual links here. So like these connectedness shapes, right? And they're very strong, right? You cannot miss an item here. But one downside of them is that we have occlusion here. So we render these lines on top of them. And so this paper was really mostly, like here you see an example with OLAP that makes it hard to read. And this paper really, we found a way to like optimize those links so that we, given a computational model of the saliency of the scene, we can route those links so that they are like not disturbing the content of the image. This is just an example of how we can leverage some of these perceptual principles to do something interesting in visualization. So the takeaways about this perception lecture is that knowing about perception is really important for visualization and more generally user interface design. How do we choose our colors? We need to be aware of like the properties of colors. Like color hue is unordered, for example. We need to be aware of things like color blindness in a large share of the population. How do we show relationships between items on the screen? How do we draw attention to something that we care about? And how do we avoid it being overlooked? How can we minimize this risk of overlooking? So that's kind of like the takeaway, and that's all that I wanted to say about perception. Any questions about perception before we move on to data? Okay, great. Let's see. Okay, so let me just do a couple of announcements. On Tuesday, we'll be talking about JavaScript and D3. So this will be kind of like giving you all the tools you need to complete homework 2. On Wednesday, we'll have our first lab that kind of like recaps some of the concepts that I talked about in the Tuesday lecture. It's going to be at 6 in L110, which is a room just on this floor here. This is, of course, voluntarily. Like, we will not tell you anything that you cannot learn from the lecture or that you cannot see from the homework instruction, but like we will just like reiterate some of the concepts. There will be like a short exercise, and then we'll just go over the homework and how to implement this, give you some strategies. So if you're familiar with JavaScript, then you probably might not need to go to the homework 2 lab, but if you're kind of new to the whole thing, then it might be good for you to go and like revisit the concepts. And then on Thursday, I'll be talking about what I like to call the visualization alphabet. What are the basic ways to encode data on the screen or on paper? And for that, we'll have this paper here. And like I always have, or frequently have mandatory readings, but this one here, I really mean that you should read it, because I will actually ask you questions in lecture about it. And this particular paper will also be on the test for all grad students. So please do read this paper, and then we'll discuss it on Thursday. Okay, so when we talk about data, we need to kind of define a little bit like some of the terms. And you'll, like, if you want to read up on all of this, this is basically taken from Tamara Mansell's book, our textbook here. So first, we have data set types and data types. So data set types are like the things that we can visualize or can be analyzed. So here we have tables, networks, fields, and geometry. And then we subdivide tables into like regular tables and multidimensional tables. And networks, we can subdivide networks in many ways, but one particular useful way is dividing them into general networks or graphs and into trees. And the data types are the fundamental units which in combination make up our data set types. And the data types are items, attributes, links, position, and grids. And so we'll start talking about items and attributes. Also, one important note is that you also, like, it's very common to distinguish between structured and unstructured data. Right? Structured data is all of this here. So this is stuff that we can easily process in a computer. Unstructured data is not really like something that we can easily process in a computer because it lacks structure. This is, we don't have a predefined data model. There isn't like, here's a label, this is the fact. This is commonly commonly found in text. Like text is unstructured, right? It contains information. It's made for humans and not for computers. Text can be interspersed with facts, things like dates or times or locations or just arguments. And the other major source of unstructured data is videos or images. And not surprisingly, there's like major fields of computer science that are concerned with extracting structure from these unstructured data types, right? NLP is all about getting structure out of unstructured textual data. Computer vision is all about getting structure out of video and images. So what we will do in this lecture is we will mostly assume that the data we worked with is structured. So we kind of like, we're not talking about any NLP approaches. We assume that this has been done for us and we have a structured data set to work with. Here's an example of what you could do with a very simple extraction algorithm from text. This is like a paper from, I think, 2009 that's called phrase nets, and that's kind of like a trivial NLP thing that's happening here. Basically, they scan, in this example here, the Bible for a particular pattern, like X begat Y. So for those of you who are like not native English speakers, beget means basically had a child or like fathered or like mothered. And by just like parsing for this simple rule, we can extract family relationships out of the Bible, right? And so this is what we have here, like, well, where isn't something that we all would know? Abraham beget Isaac, beget Jacob, beget Joseph, and so on. So we can kind of like extract structured data from an unstructured data source by like different rules of different complexity. Yes?
Out of curiosity, what is the size of each?
The frequency of the terms, how frequently they occur in the Bible. I think. I haven't read the paper, but it's kind of weird, right? These are not characters we would know that well, but I would just have to look it up in this paper. But frequency would be a very common thing. Maybe it's also the node degree, but no, that wouldn't make sense here. So I'm guessing it's a frequency. You can kind of like use a different way of specifying the rules. So for example, if you say X is Y, and you run this on 18th and 19th century novels, then you would get something like quite interesting here. So for example, we have the wife, and the wife's like the father's wife, the apothecary's wife, the ambassador's wife, the officer's wife, the merchant's wife. Whereas if we have bride, like less honorable, we have the freebooter's bride, the bandit's bride, the outlaw's bride, the sailor's bride, the pirate's bride, right? So we can look at these kinds of patterns with these very simple, algorithms, and this is kind of like we can create the structure if we need to. And I'll talk more about things like this in our lecture on text and document visualization. Okay, now let's take a step back. One thing that's super important when we talk about data is the semantics of the data. So Basel 7S pair. It's a valid data vector, right? What does it mean? Could be things like basil could be the plant, 7 could be, I don't know, I need 7 basils, and then I need small pears in my shopping list, right? We don't know, but if we provide the semantics then, and we provide the real world meaning, we can kind of like understand that. So we need this metadata to interpret the data. And in a tabular data set, that's usually the table header. So we have like name, age, shirt size, and favorite fruit, and now we have clarified what this vector means. Right? And it's like simple and completely intuitive, but still worth reminding everybody that we always need to provide the semantics so that we can actually interpret the data. When we talk about data types, in this lecture particularly, what I mean is really not the structural, it's the structural or mathematical interpretation, but not data types in programming, right? I'm not talking here about ints or floats or anything like that. I'm talking about something that is a little bit higher level. So for example, an int could be used as a link because it points to another ID. So like this is a little bit different. And so the data types here are item, link, attribute, position, and grid. And we'll go over them one by one, but item is essentially, item and attributes are in tables, links is in networks, and position and grids are in these like fields or grids on themselves. So let's review them. So items are individual entities, and they're typically, or they are discrete. So for example, things like patients, cars, stocks, cities, or hospital visits, or like specific events. And in statistics, you often call these the independent variables. And the attributes that go along with these items are measured, like measured properties of the items. They are like observed about these items, or we log their property. So for example, if we have a patient, the attribute would be patient height, blood pressure. If we have a car, the item would be a car. We have the attributes horsepower, make. And this is what we usually in statistics refer to as the dependent variable. Dependent variables because the values of the attributes depend on the independent variable. And so here, what are our items?
Your item is your ID.
The items are not the IDs. It's the person, right? It's like, it's not the one field here, it's the concept of like, who are they? It's like each row corresponds to an item, and each row here corresponds to a person. And the attributes are name, age, shirt size, favorite fruit. So these are our attributes here. The other data types here are links, and links is something that expresses relationships between two items, right? So if we had, in this example, we could have like another column that says best friend, and then we could have somebody else's ID that would be a link, right? And that doesn't really fit well into our model of items and attributes. So this is something that is distinct and that we treat distinctly. Examples are friendships on Facebook, so friendships in real life, or like knowing somebody, like networks basically. And like this is a massive data type and research area. You can have like this in the science of things like interaction between proteins, or like predator-prey relationships in ecology. Another data type that we care about is positions. They are also distinct. Like here, we talk about spatial data. It could be something like the location in 2D or 3D, or it could be the pixels in a photo, or the voxels in an MRI scan, or latitude and longitude on a map. And then finally, grids is a sampling strategy for continuous data. And so we can kind of like, if we have a continuous data, like temperature across the surface of the United States, or elevation across the surface of the United States, or like the temperature in a combustion engine in a 3D volume, then we need some grid so we can get discrete representations of this continuous data. And the things that we care about here is how many like voxels do we have in an MRI scans, or how many weather stations do we have in the United States, and how do we sample this? Okay, let's talk a little bit on a higher level about data set types and start out with tables. So the most common thing, like what we've already seen before, is our flat tables, where we have a single item per row, and each column is an attribute. All tables have a key, and that is unique. It can be implicit. It can just be the row index, right? So you see that frequently, that simply the order is used as the key. And like at least in this strong definition of what a flat table is, I do not want to have duplicates in there. A multidimensional table is a table where I need to index based on multiple keys. So think about, I have a column, and I have rows and columns, and I need both keys, and I could have multiple tables even on top of each other. And so I need to first index into which table, then into which row, then into which column. So here is a flat table example again, where we have one item per row, and then our values in the rows. In here, and then our key here is explicit. The ID here is our key. This is an example of a multidimensional table. This is like gene expression versus sample ID. So I have to look up gene name versus like which sample was that to find something. Like here we have another key, the patients, and then here we have the key of the genes. And then we could even like stack multiple of those tables on top of each other for different data types or for different time points, right? If we have collected this data at different time points. And so to really specify an individual cell, we would have to specify which table, which column, which row. So how can I visualize tables? Right? We'll have a full 2 lectures on visualizing tables in high-dimensional data. Here are just 2 examples, a parallel coordinate plot and these kind of like tabular bubble charts here. So we'll talk about what that means and how this works in the tabular visualization lectures. Another thing that we need to be aware of are collections. They're kind of like another data type in some way, but they're usually like an additional way of thinking about the data. How do we group the items in addition to just as a list in or just as like in the flat table? And so one way to group items would be in sets, and like as you all know from math, sets are unique, contain unique items, but items in a set are considered to be unordered. Contrast to that, lists is where we have like something that is ordered and where we do allow duplicates. And then like it's useful to also think about clusters. Clusters and sets are very related. Usually my distinction here is that clusters expresses some kind of like not objective similarity, whereas a set is something that is like really hard-coded. So like it's whatever I have like restaurants versus subway stations, that's a set distinction, right? But if I want to classify the points in this scatter plot here, I could, like it's not completely clear where do these points at these intersections here belong, where do these points here belong. So I have the softer notions of clusters that are groups of similar items. And we'll talk about, we'll have a dedicated lecture on set visualization. We'll talk about clustering when we talk about tabular data and so on. Graphs and networks are, like the definition of a graph is that it consists of a set of vertices, which are also called nodes, and a set of edges, which are also called links, that connect these vertices, right? And this is like where we use the link data type to like make these connections. Here's a simple example. A special type of graph is a tree, and like in mathematical terms, a tree is simply a graph with no cycles. So that's sufficient for like the tree definition in graph theory. In practice, when we think about a tree, we very frequently think of it to be rooted and directed. So we have like an organization chart, or who you report to in an organization could be a tree, and that is usually directed and rooted. So here is an example of a rooted and directed tree. But the thing is, like, there's no cycles, so there's always a unique path between 2 items in a tree. And the properties of trees allow us to use different visual encodings than for graphs, right? So we kind of like, by having this restriction on the topology, we can use more efficient visual encodings to unambiguously encode a tree. So here are some examples, and we'll have 2 lectures on graphs and trees. So here, like the classical node link diagram, here's an adjacency matrix which represents the same data. If you don't know those techniques, it's fine, I'll talk about them in detail. And then here on the right, we have a tree map, which is an implicit tree visualization. So here we have like the full-on tree structure of like who imported coffee, and we have attributes on top of this network. I already mentioned like fields and what the point about continuous data is. Here we have attribute values that are associated with cells, and these cells contain data from the continuous domain. And these are usually as a natural observation, things like temperature, pressure, wind velocity, or anything like that. We can have fields either measured or simulated, usually to deal with fields, especially to the measured ones, we have to really think about sampling and interpolation, because our method of like measurement cannot never be perfect, right? We'll always have some gaps in how we measure them. And so this is really the topic of signal processing and statistics, is where you cover things like that. And so like what you see here, this is a map of all the weather stations in the United States. And you see also some background information, rural, like suburbs and urban. And what you see is this isn't like nobody like ever tried or never thought it would be a good idea to have like a uniform sampling of weather stations across the United States, right? We care much more about like variation if it's a densely populated area, when the environment, like it's close to like a lake or close to mountains, then we need a little bit more data points to sample. Like in Utah here, you see the classical Wasatch corridor here, where we have lots of these stations, and then there's not really any official weather stations in western Utah. But then we kind of like create visualizations like this that give the impression of continuous data, right? So this is an air quality map from like airnow.gov. And like, as you know, Utah has a little bit of an air quality problem, but that particular day in 2017, it was just fine in Utah. But of course, the data here isn't continuous, right? It's interpolated based on like very few measurement stations, right? Where first we have the uniform grid, where we simply can compute both the geometry and the topology. So we don't actually need to store any information about the grid. We just need to store the rules how the grid was constructed. A rectilinear grid is when we do something like here, where we have non-uniform sampling, right? So if we know that we care more about some of the areas, we can do this non-uniform sampling. A structured grid would be things that allow a curvilinear grid, like here. So this is still a structure, but it is like it has also these like curvilinear shapes allowed, and then the most flexible way to sample a field is an unstructured grid. Here I have full flexibility, but I do have to store everything about the grid in addition to the data that I sample on top of it. And so you'll talk more about this, if you take the visualization for scientific data class, this kind of stuff will be kind of the main content. This is what you need to do if you want to visualize something like this MRI scan of the head and the torso. We do talk a little bit about visualizing fields in the context of maps. So here's like a wind map on top of the United States, and so we'll cover some of that. I just wanted to add a side note, especially if you're like considering visualization as a research area for yourself in the future. There are three different academic subfields of visualization. It's called, one is information visualization, what's about abstract data, things like tables, graphs, and maps. What's unique about them is, except for maps, you're really free to mostly choose a spatial layout. And so this is really like what we cover in this lecture mostly. It also covers perception research. And the second one is visual analytics, and we also cover that here. That is basically InfoVis plus stats plus machine learning plus applications plus building systems. And so people have basically created the field of visualization, and now I'm being a little bit ironic to get like NSF and other agencies like DARPA to open up the faucet and give them more money. This kind of happened post 9/11 mostly, and so like, now we have visual analytics as this field, especially for intelligence analysis, but now it's much broader than that. So the boundaries here are not very clear. And then we have scientific visualization, which is all about spatial data, which is kind of the oldest subfield. Like that's kind of how visualization started, and that kind of is very closely related to computer graphics. Here you're typically not free to choose a spatial layout because you have this continuous data, and it's really about finding the best way to depict reality. And the problems that you care about here are some kind of like mathematical description, things like ray casting, or like ways to like build things like transfer functions. And another thing that is now very important is scalability. Like what if you have multi-terabyte simulations? That's a big deal in the scientific visualization community. So if you wanted to build a trivial classifier to know whether a visualization is scientific visualization or information visualization, like this is what you need to beat. InfoVis usually has a white background, scientific visualization usually has a black background. The reasons behind that is probably like the closeness to computer graphics, right, and like rendering in scientific visualization, and like the closeness to design and like different tools that we use, and to journalism and information visualization. Okay, so enough of the detour. If we talk about geometry, we talk about the shape of items. Here we have explicit spatial positions, things like points, lines, curves, surfaces, regions, or volumes. We will touch this mostly when we load like maps, but we will not cover that in like so much detail. It's not really a core visualization topic. It's more of like computer graphics and like CAD problems. We do use them. Like we use geometry, but usually geometry is like the base layer, and then we add data on top of geometry. Okay, so now I want to do a design critique. I'll give this handout in a second. Here's also a link if you want to follow that, but let me just play this video and I go back to the slide.
Hi, I'm Michael Ogala, creator of CodeSwarm. This video is meant to be a companion to our paper, so it assumes some basic knowledge about our visualization technique. Due to the size limitation on videos, we cannot cover everything we wanted to. For the full story, please visit the CodeSwarm website to see the original videos. The story of Python begins with Guido Mandrasso, working alone in the late 1980s. He is Python's creator and benevolent dictator for life. A year later, 2 developers join him, but they stay on the periphery of the swarm. One of them, Jack Jansen, created MacPython. His activity stands out because his sphere of influence periodically converges and diverges with Guido's. Another person, Fred Drake, appears and commits mostly blue document files. Indeed, he will become the lead documenter of Python. This pattern of Guido being the clear central developer with specialists on the periphery continues. In the year 2000, the popularity of Python takes off. We see many new developers coming in as the project activity increases dramatically. And for the rest of the video, the project stays busy. The Eclipse project is vastly different than Python. Right away, there is a flurry of activity. Many developers working on many files at nearly a constant pace. This is possible because these people were already working on the same project before Eclipse was open sourced. We also see that, even amid the chaos, the Eclipse project is made of many components. There are many developers clustering around the center, yet they each have their own set of files. In other words, there is not one large set of files being worked on by everybody, but many small sets of files being worked on by individuals. This can be attributed to Eclipse's rich client platform, which facilitates modular design. Looking at the commit histogram, we see something not apparent in the Python video: weekends and holidays. Weekends are the periodic gaps in the histogram occurring every 7 days. The holidays can be seen at the end of December throughout the video. These breaks further reinforce the idea that Eclipse is developed with corporate sponsorship.
Okay, so I'm going to skip the rest of the video. I have another handout for you guys. And I'd like to kind of look at this and again in the group discuss things like who is the intended audience, what questions does the visualization answer, what data is represented, how is the data visually encoded, can you read it precisely, and then why is this visualization technique, why was it super popular back when it was when it appeared, and also some personal opinions. So here's the link if you want to access it on the device.
The first thing that I noticed was they actually have music in most recently.
Using like shapes, has anyone ever tried using like faces between the faces?
Yes, it's called channel faces. And it's a terrible idea.
I was thinking about like hacking that, just like exploiting humans.
Yeah, this is exactly the reason we did channel faces, and people have studied this in detail and shown that they don't work. The problem is we are good at recognizing differences, but not at their meaning, right? Like, what does it mean that I have closer eyes versus like higher eyebrows and so on?
They did say that.
Are these scientific visualizations or are these?
It's not a perfect classifier.
So let's see, who is the intended audience? Well, it has black background, right? So it must be scientific. So this must be graphics people, people this people. Yeah, that's the question says visualization answer. It's mainly targeting activity. Look at locations. Or the development of the project, who's developing it. Because whoever connects the mouse must be the most important person in the project.
The goal is to have a timeline of when all these apps are
What data is represented in this visualization? It looks like it's size and frequency. So it's encoded by the brightness of the dots, brightness and size of the dots. Or no, brightness, size, and what do you call it?
Brightness of the name.
And also the distance, like the percentage and read with the sometimes we disagree. So the so it may be right. Can you read the data precisely? So There's a funny chef who is the so you see, we don't at all in it.
I got me inspired to do a bunch of like my name on
You know, some using your username, you can ask to use perfect picture. Profile picture.
I don't know how they like overlap that. They want the names to like overlap too.
So you know, it's probably easier just like a bunch of circles and little blobs.
As you can see, when the video was going, we were not actually focusing on me portrait, focusing on the position of the photo. Sometimes there will be faces will be distracted.
What is this like the blue versus the red?
This one is not red, this one is equals. So it's the blue guys, there must be 2 different hair bases.
I think in the middle, right now, you can't see more information. So much.
Well, you know, GitHub's not using it as a visualization, which means it's probably good. So you see the visualizer for GitHub? It's just one line chart. So you
Like dotted lines.
Oh yeah.
yeah. But the other thing was you can see who's adding, who's deleting stuff. So the people who delete stuff are usually the code reviewers and people who are adding stuff. Contributors.
And also, there are a lot of things going on in the video, so you cannot focus on one topic because maybe you will have something like that. So it's having to use the composition, you cannot be specific about that.
Well, yeah, I think they're trying to, they wanted to see what people who show up. Who has it?
It looks like we're right. I want to see the sun a lot.
Yeah, it was very
I see the others. Well, so things like so that's yeah, that's you must have added some unique change to one file.
It's like a bright red dot.
Okay, so what does everybody think? What's the audience of this particular visualization?
We thought program managers and developers.
Program managers and developers? Anybody else have an idea?
It's just a university project. The target audience may also have been like their professors and other students in the same kind of visualization program as them.
Yeah, if you think about it this way, it could also be the paper reviewers. Yeah. So, like, what do you think about the distinction between programming managers and program managers, product managers, and developers? Like, who do you think this is really more interesting for? Developers. Why?
talk about.
Can you raise your hands? Like, why?
Developers want glory, and developers with glory.
So what you're saying is essentially this is a little bit of navel gazing, kind of like for like an open source project, like oh look what we did.
I think because it shows how particular programming came into picture and who was involved and contributed to it. So developers are more keen on knowing okay who was involved and how.
Yeah.
Not everybody's.
Yeah, for like a program manager to evaluate the performance of one of their developers, would that be a good tool? No. No. Okay, so what kind of questions does this visualization answer?
So like at a given time, a person's like involvement, productivity, and contribution.
Yes. So we have like time point. How is time represented?
It's like through the video.
Yeah, so it's animated. Time is mapped to time. Yeah.
How the popularity of various frameworks and languages grew.
Exactly. So if we had multiple videos, we could look at how does like this project, how did it grow in popularity? We're measuring here popularity not by the number of people who use it, but the number of people who contribute to it, right? So this is going to be very distinct for an open source project to like a closed source project, where like the number of people that work on it really is driven by the company that develops it. So okay, let's break this down a little bit more into data types. So what are the data types here? Like what are the items? Two different types. Yeah. Commits. Commits might be an attribute, but what are you committing?
Files.
Files, yes. So one of the items here are files.
And developers.
And developers. So we have people and developers, people and files as our data as our items. And so what are the attributes that we observe about those?
Types of files.
Exactly. So the type and the file and the change, right? So like there's two things here. We have the types. How is the type encoded? Color. Yes. So the distinction here is pretty rough, right? It seems to be mostly, at least in the Python example, it's source code versus documentation. There's like, if you look at this video and the slides, there's later they talk about the game, and then you have like artwork as well as a distinct file type. What is the relationship between those two different items, the developers and the files? How is that encoded?
Files are little dots in a circle around the developer's name.
Exactly, and so we can say this is essentially position, right? We have the developer and the files that they're working to with are like positioned around the person. Okay, so like, is this like, can you read off the values here precisely? Like, could you tell how many editors Guido van Rossum made to Python? No. Why isn't this a problem? Like, why is this okay for this visualization and not be precise? Yeah.
Very narrative driven, so we're kind of talking through the story of Python while it's playing out.
Exactly. It's more of like telling like a higher narrative arc and less about looking at the individual data items. And the authors of this paper kind of like coined the term organic visualization to kind of like try to like start a movement of like visualizations that are really more about like telling a story, like communicating a mood, communicating some events, and less about making this as precisely readable as possible. So why do you think people like this particular tool quite well?
It looks pretty.
Looks pretty.
The storytelling?
The storytelling aspect, yes. And I think even more important, the storytelling aspect, you could actually, I don't know whether this was obvious, but you can like load your like this was published a while ago, so back then a Subversion repository into this tool and it would automatically generate them, right? It wasn't just storytelling for some other project, some other person's project, but you could do this for your own project. So you could kind of like, if you're like the development team behind the project, you could put a video of this on your website and kind of communicate the activity and the story of your project. And obviously, that leads people to care about this. And so, like, what do you think about this visualization? Is this like a good visualization, a bad visualization? Other comments?
Depends on what you're using it for.
Yes, so it depends on the task. It's the easy answer for every visualization, whether it's good or not. But I agree, it just really depends. Yeah.
I don't think there are many tasks where this is actually very useful.
Yeah, so you might argue that this is really like a novelty thing, right? People enjoy watching it once. It's really like not like a tool for like analysis that you would revisit frequently. But you're able to see some like patterns, like you can characterize projects and so on. Okay, this wraps it up for today. I only have 10 slides left for data, so we'll just squeeze them in next time. Tuesday we'll talk about the basics of JavaScript.